Welcome to today's deep dive. I'm your host, and I'll be guiding us through today's architectural breakdown.
And I'm the resident cloud architecture expert. Really glad to be here to unpack this one with you.
So I still remember the very first time I saw a production dashboard turn completely red.
Oh, yeah. It's a visceral feeling.
It really is. And it wasn't a slow fade either. It was just instant. 1 minute, traffic is humming, the CPU is happy. The next minute, latency spikes through the roof, the load balancers start screaming, and your Slack channels just light up with people asking, is the checkout down?
Usually right in the middle of a massive flash sale or a big product launch.
Always. Always when you need it most. And the worst part of that specific outage I'm thinking of, it wasn't even the core service that failed. It was some third-party API for calculating shipping rates that just timed out.
Ouch.
Yeah. But because we hadn't isolated it, it dragged the entire checkout process right down into the abyss with it.
That right there is the classic tight coupling nightmare. You think you've built this robust castle, but you've actually built a house of cards where if the wind blows on the shipping calculator, the whole payment gateway collapses.
Exactly. And that is the exact mission we are on for this deep dive.
Yeah.
We're going to talk about fixing that fundamental architectural flaw, tight coupling.
It's such an important topic for anyone building systems today.
It really is. And to do this, we're looking at a fantastic piece from the Tech Reader blog by Aaron Rose. It's titled The Secret Life of AWS, the Buffer Amazon SQS.
It's a great read because it doesn't just, list off AWS features in a vacuum. It frames the whole discussion around a narrative.
Right, a narrative of fixing a broken system that looks suspiciously like the one I just described.
Yeah, Rose introduces us to two really relatable characters. There's Timothy, the builder, who is currently watching his microservices burn to the ground.
And Margaret, the mentor who's going to show him the way out.
But before we get to Margaret's solution, we really need to understand the crime scene. We need to look at the anatomy of this crash.
Okay, so let's set the stage. Timothy has a microservices architecture. On paper, it looks totally fine. He's got a checkout microservice and an inventory microservice.
Both hosted in AWS, and they're connected via an AWS transit gateway. So network-wise, the pipes are totally secure.
But the logic is where the trap is hiding. The article describes a specific failure mode. There's a traffic spike, which causes the inventory database to lock up.
Which is pretty standard stuff, right? Too many concurrent reads and writes, and the database just stalls.
Right. But instead of just the inventory service failing, the checkout service crashes too.
And this is where we need to explain the synchronous trap. Timothy wired these two services together using a standard synchronous REST API call.
Which, that's the default for most developers.
Yeah.
It's how we naturally think. I ask a question, I wait for an answer. It's linear.
It is super intuitive. Checkout essentially says, hey, inventory, deduct item X. And then it stops processing. It literally holds the network connection open, waiting for that HTTP 200 OK response to confirm the deed is done.
Waiting for the green light.
Exactly. But in a distributed system, waiting is a dangerous game. If the inventory database is locked up, it's not sending any response. So checkout just hangs there.
It hangs until the connection finally times out.
Right. And here's the resource implication that often gets completely overlooked. Every one of those waiting connections is consuming a thread in the checkout service's compute pool. Memory, CPU cycles, they're all being held hostage by a request that simply isn't moving.
So you get thread starvation.
Exactly. You could have a massive fleet of servers running your checkout service, but if every single compute thread is stuck waiting on a timeout from inventory, you have zero capacity to take a new order.
The door is effectively nailed shut.
Yep. Margaret calls this a rigid chain. And it's such a perfect visual for tight coupling. You've handcuffed your healthy service to your sixth service. If service B fails, service A fails right along with it.
If one jumps off a cliff, the other one is going with it.
Back.
Now, Timothy's initial defense in the story is really interesting, and it's something I hear a lot. He thought a secure network was enough to make it robust.
That's a huge misconception. Security does not equal resilience.
Right. And he also argues with Margaret. He says, but I need the stock to be deducted. I can't tell the customer the order is complete until I know we actually have the item in the warehouse.
Which feels like a completely valid concern. We want to prioritize consistency. We want to be sure we aren't selling things we don't have.
But Margaret flips the script on him here.
She does. She introduces a massive paradigm shift. She tells him to move away from synchronous communication and embrace asynchronous communication.
Moving from please do this and tell me when you're done
to here is an instruction, handle it when you can.
And this brings us to the hero of our deep dive, Amazon's Simple Queue service. or SQS.
The shock absorber.
Yes, the buffer. So let's walk through what this decoupled workflow actually looks like. We are breaking that rigid chain. Checkout no longer calls inventory directly.
Not at all. Now, when a customer clicks buy, the checkout service just constructs a message, basically a JSON payload that says, order 123 purchased item X.
And it drops that message into an SQS queue.
And crucially, SQS acknowledges receipt of that message almost instantly. We're talking milliseconds.
And as soon as SQS says, I've got the message, checkout immediately returns a 200 OK success response to the customer.
Checkout's job is done. It is now completely independent of whatever is happening with the inventory database.
Now, let me play devil's advocate for a second here. From the customer's perspective, I see a screen that says order confirmed. But technically, the inventory hasn't actually been touched yet. The database hasn't been updated.
That's true.
Isn't there a risk there?
There is a slight trade-off in strict immediate consistency, yes. But think about the user experience. Would you rather sit there watching a spinning wheel for 10 seconds that might eventually crash?
Right.
Or would you rather get an instant confirmation? The system has captured your intent to buy perfectly. The actual back-end processing just happens asynchronously behind the scenes.
I like to think of it like the text message model. If I call you on the phone and you don't pick up, I'm stuck holding the line. But if I text you, I hit send and I just go back to my life. I trust the network will deliver it eventually.
And in this context, eventually is usually just a few hundred milliseconds later. But that decoupling changes the game for the checkout service. Inventory could be completely offline, on fire, or rebooting.
And checkout just keeps happily accepting orders and dropping them into the SQS queue.
That's the buffer working. SQS absorbs the shock.
Okay, so the queue can fill up with 10,000 messages and checkout doesn't care. But we have to talk about the mechanics on the other side of the queue.
Right, because a bucket full of unfulfilled orders doesn't do the business any good.
Exactly. In the old model, inventory was passive. It just sat there waiting to be poked by a synchronous REST call.
But now the behavior totally flips. The inventory service becomes a consumer. It actively reaches out to SQS and says, hey, do you have any work for me?
Which is polling.
Right, polling. But Margaret gives Timothy a crucial efficiency tip here. If you just write a script that screams, any mail, any mail, any mail, at SQS 10 times a second, you are going to burn through your AWS budget.
Because you pay for those API requests, even if the queue is empty.
You do. SQS will happily charge you for returning empty-handed. Plus, you're burning compute cycles on your own servers processing those empty responses.
Which is where Margaret introduces long polling.
Yes. Long polling is essentially smart waiting.
Walk us through how that works.
When the inventory service asks SQS for a message, it says, I'm going to keep this network connection open for up to 20 seconds. If a message arrives in the queue during that 20 seconds, give it to me immediately.
And if not?
If not, the connection simply closes gracefully and the inventory service tries again.
So instead of making thousands of frantic, empty calls every minute, you make a handful of sustained ones.
It drastically reduces the chatter on your network and the size of your bill at the end of the month.
That's a massive optimization. But there is a trickier mechanic we need to unpack here, the visibility timeout.
This is a critical feature, and it trips up a lot of people when they first start working with message queues.
Well, we have to assume the inventory service isn't just one single computer sitting in a closet, right? It's probably a fleet of compute threads all trying to pull messages from the queue at the exact same time so they can process orders faster.
Right. So imagine you have server A, and it grabs order 123. It starts doing the work, calculating the tax, updating the database. That work takes time. But while it's doing that, order 123 is technically still sitting in the queue.
So what stops server B from grabbing that exact same order a millisecond later?
SQS uses a visibility timeout. When server A pulls the message, SQS essentially hides it temporarily. It starts a timer, let's say 30 seconds.
And during that 30-second window,
the message is totally invisible to server B, server C, and every other compute thread. It prevents them from grabbing the same order while the first one is working on it.
But the message isn't deleted yet.
No, it is not deleted, and that distinction is vital.
Because what if server A crashes halfway through processing the order?
Exactly. If the message was deleted the second it was pulled and then the server crashed, that order is gone forever.
The customer paid, but Business has no record of it.
Absolute worst case scenario.
Hmm.
But with the visibility timeout, if server A crashes and fails to explicitly tell SQS, hey, I'm done, delete this message, that 30-second timer eventually runs out.
And the message just reappears in the queue.
It becomes visible again. Then server B can grab it and process it successfully.
That is incredibly resilient. No dropped orders. But it brings up a scary what-if scenario. What if the inventory database locks up again?
Well, if the database goes down, checkout doesn't notice. Checkout keeps dropping messages into SQS.
And SQS is highly durable, right?
Okay.
It stores those messages securely across multiple availability zones.
Exactly. So you just build up a backlog. And when the inventory database comes back online, the inventory service simply starts polling again. It processes the backlog at its own pace. 0 dropped orders.
That's the beauty of decoupling. But let's look at another what-if. What if the message itself is the reason the server is crashing?
You are talking about poison pills.
I love that term, poison pills.
It sounds dramatic, but it's really just bad data. It's a message that is malformed in a very specific way that causes the consumer application to crash.
Like a weird special character in the address field that the legacy database just rejects?
Exactly. So think about what happens. Server A grabs the poison pill, it tries to process it, hits the bad character, and crashes.
The visibility timeout expires.
The message reappears in the queue.
Server B grabs it, crashes.
Timeout expires. Reappears.
It's an infinite loop of death. You could theoretically take down your entire fleet of inventory servers with one bad JSON file because they all just keep choking on the exact same pill.
Which is why you have to use a dead letter queue or a DL queue.
How does the DLQ solve that?
Margaret explains to Timothy that you can configure SQS to essentially count the failures. You set a threshold. You say, if this specific message has been pulled and failed 3 times, stop putting it back in the main queue.
Just yank it out of circulation.
Right. SQS automatically moves it over to a secondary queue, the DL queue. This unblocks the main pipe so all the valid, healthy orders can keep flowing through.
But you can't just leave them in the DL queue forever.
Right.
And those are still real customers who tried to buy something.
No, you can't. You need a manual inspection process. An engineer has to actually go into the DL queue, look at the payload, figure out why it broke the code, fix the bug, and then replay the message.
It basically converts a system-wide catastrophic outage into a standard bug report.
That is exactly what it does.
So far, this all sounds like a magic bullet. We've decoupled the systems, we're handling database crashes smoothly, we're dealing with poison pills, we're saving money with long polling.
It is a massive improvement, but Margaret does warn Timothy about one catch at the very end.
The catch is idempotency.
Yes, idempotency.
Now, this is a concept that I feel really separates the junior architects from the senior ones.
It really does. It sounds like a complicated mathematical term, but the problem it solves is actually quite straightforward. You remember that visibility timeout we just talked about?
Right, the timer that hides the message.
Well, SQS guarantees what they call at least once delivery.
At least once.
Meaning, the standard behavior is to deliver a message exactly once. But in very rare cases, a message might actually arrive twice.
How does that happen?
So server A processes the order perfectly, but right as it sends the delete command back to SQS, there is a tiny network blip.
So SQS never gets the memo that the job is done.
Exactly. SQS thinks server A failed. The timeout expires, the message reappears, and server B grabs it.
And now server B is happily processing an order that server A already finished.
So you deduct the inventory twice for the same purchase.
Which is terrible. You're ruining your inventory counts.
Right. This is why Margaret stresses that the application logic itself must be idempotent.
Break down idempotency for our listeners. What does that actually mean in code?
It means you must write your code so that processing the exact same order ID multiple times does not result in multiple deductions. The end state has to be the same, whether you process it once or 100 times.
So you can't just write a blind command that says subtract 1 from stock.
No. The inventory service has to be smarter. When it receives order 123, it has to check a state store first. It has to ask the database, hey, have I already processed order 123?
And if it has, it just drops the duplicate message and moves on.
Exactly. But you have to be careful. That check has to be atomic.
Right, because you don't want race conditions where server A and server B both check at the exact same millisecond, both see it hasn't been processed, and both deduct the stock.
Spot on. So you end up using things like conditional writes in DynamoDB or unique constraints on a SQL table. You architect it so the database simply rejects the second attempt to process that specific ID.
That definitely adds complexity to the application layer. You're trading a very simple API call for a transaction that requires safeguards, state lookups, and error handling.
It is a trade-off. It absolutely requires more upfront engineering work.
Timothy realizes this. He can't just plug in SQS and go to lunch. He has to actually rewrite how his application handles data.
But the alternative is a system that cascades into failure the second a dependency gets slow.
Right. Complexity in your application code is the price you gladly pay for true resilience in your architecture. Once you build an idempotent system, you stop waking up in a panic about network blips because your code is built to handle duplicates safely.
So if we zoom out and look at the whole journey, we've gone from a fragile, synchronous, tightly coupled mess.
To a robust, asynchronous, loosely coupled success.
We've moved from relying on rigid chains to utilizing architectural buffers.
And the real value here is isolation. You are isolating failure. One bad service or one locked database doesn't take down the entire business anymore, which is the holy grail of distributed systems. And it brings me to a final provocative thought for everyone listening. Margaret highlights a profound philosophical shift in this story.
She really does.
In a distributed world, whether you are dealing with microservices or even just human teams working together across time zones, you simply cannot assume things will work perfectly.
You have to design for the assumption that dependencies will fail.
Exactly. So look at your current architecture or even your current team workflow. Does it sit around rigidly waiting for permission and a 200 OK response? Or does it drop a message into a buffer and confidently move on to the next task?
That is the question you have to ask yourself.
Well, on that note, I think I'm going to go check my own message queues. Thanks for joining me on this deep dive into the secret life of AWS.
Anytime. See you on the next one.